Hello. Hi. Oh, that. Hello. Hello. Hi. Hi. Hello. Hi, Sean. Hi, Maisha. Hi, Lizzie. Hi, everyone. Hi, May. Hi, Eric. Hello, Eric. And great job, Eric. Anyway, hello, Noel. Hello, Elizabeth with an S. Good to see you all. And yes, good to see you all. Okay, yes, good. Hi, hi. Huh, wait. Oh, did I not say, oh, hello, Jayla, I'm sorry. Oh, and also, wait, I'm sorry, yes, hello, Jayla, and did I say new, oh, hello, Noel, who else did I say? And hello, Stephanie, did I not say hello, I'm sorry. Wait, really? Huh, okay, that's interesting. Thank you. I don't, that's good. So I guess that means you studied, or you, okay, no, I'm glad you used the channel for maybe, yeah, no, okay, great. You know, I often do forget, I should pay attention to views. Thank you. I haven't actually looked for, okay, but good. I appreciate, I hope they were useful. Wait, and someone just came. I'm sorry, I'm a little bit, hold on. Wait, what just happened? I thought someone just came. Oh, yes, someone did. Okay. Okay. Um, and sorry. Oh, I'm very glad to hear that, Maisha. And even if, I mean, no, I am glad to hear that, whether we're being polite or not. I mean, thank you. But either, if it's true, thank you. And if you're being polite, thank you. Either way. And actually, but I mean, obviously, I'm selfishly glad to think if the YouTubes are useful at all, that is terrific. But also, actually, okay, that there's something. Oh, that's interesting. Okay, no, this is good to know. And in fact, speaking of that, okay, no, that is good to know. Sorry, I'm a little stuttery at the moment because have we met? Oh, wait, right. Okay, sorry, hold on for 1 second, because hold on for 1 second. Hold on. One second. Pardon me for once. I see the questions in the chat. Just hang on to things are happening in the chat, both publicly and directly. So give me a moment, everybody, for a second. Sorry, there's more than one thing happening in the chat. Just give me a moment for a second. I apologize. Yeah, just give me a second. Okay. Once, okay, I'm looking at the chat. Again, there's more than one thing happening in the chat, both publicly and privately. It's all significant and it's all like not jokes. So just give me another second. Okay, here's the deal. Okay, there's one question in. All right, there's a number of things I want to say. I'm glad you're all here. You all are here. Okay, I'm glad that all of you who are here are here. Let me answer one question in the chat, first of all. Today, we're not going to go over the questions in the midterm right now. We're not, and there's reasons for that. We certainly, we're not going to go over specific questions in the exam right now. There are a couple of reasons for that. I will get to that in a second. We certainly will, I think we will Wednesday, but at worst after break. Let me say a couple of things about the exam and what's going to happen for the rest of the semester and stuff like that. Okay. So first of all, I know, I think, how can I say this? Okay, look, first of all, the exam did go the way I was hoping for all of you in this sense. All of the sections, the exam was due at the same time. All of the sections, the exam was due at 12:15 today. In all of the sections, to be clear, I mean, in every single one of the sections, including the one that doesn't even meet till tomorrow, in every one of the sections, there were certain things that happened with certain individuals, like certain issues that arose, and those individuals have communicated with me as I requested or as I was hoping. So in other words, at least for everybody who's sitting in this room right now, I don't have any mystery about what's going on with any of you, and none of you in the room right now has any mystery. Like if there was a particular issue with any one of you individuals sitting in the room right now, you have communicated with me, which I appreciate, which means a lot. Like you've sort of faced the music, whatever, and you're here right now, which takes a lot. So to be honest, in all of the sections, there's a couple of exams that still haven't come in. That is one of the reasons I'm not going to discuss it right now. Okay. And again, those individuals like know who they are and like they've communicated with me, which is like the really important thing. So again, I'm saying to all of you in the room right now, first of all, I want to thank you and congratulate you that there's not one mystery in my mind surrounding any one of you. And there's not one of you sitting in, there literally is not one of you sitting in the room right now who's just like dropping an exam on my plate like 5 hours after everybody else's or a day after without any acknowledgement or explanation or request or anything like that. In other words, none of you is just presumptuously treating all of the rest of you as somehow less special, if you know what I'm saying. And again, and I want to say, I think that's really important. Like there's not one of you who sitting here right now who's just like assuming that their situation is somehow special, you know, so special that it doesn't even require communication with me. Okay. So number one. Number two, I've heard all weekend, all weekend I was getting a bunch of comments, questions, feedback, not from every single one of you, but from a bunch of you across the sections. And every single thing that I got from any one of you, even if I said I couldn't answer it, which sometimes happened, like even if I got a question that said, I can't really help you with that, like we're too into the exam or whatever, there was not one question that I got that was like rude or presumptuous or anything like that. Like all of the questions were totally thoughtful, showed that you're all either working or worried about the work and need to be working about it later or something. Like basically all of you are demonstrating like total integrity and sort of intellectual courage to face this. And it's a hard exam. And and of course, in some ways it might seem easier because it's open, universal, and all that, but in some ways it's also quite honestly more stressful because it never ends until it ends, right? Like it's not just like it's over in 3 hours. It's not over until you hand it in to me. So So, and I've had all different kinds of exams in my life as a student. And I want you to know that this kind of exam, I probably would have thought that I would want more than certain others. But then once it started opening up, or once it came to the doing it, and once I saw little weird things in it that were a little bit different from the practice exam, like seconds over meters or something like that, which are okay, or little things, they would really stress me out. And especially if I thought, oh my God, because he knows I can do everything, like I've got to do this perfectly or something, I would find it very stressful. And at certain points in my studenthood, I might even be the kind of person that might, for one reason or another, really not want to show up today. Maybe I would turn in the exam and not want to show up, or maybe I would not want to show up because I didn't want to turn in the exam. Whatever it is, I think it actually takes facing the music, and it takes some sort of courage and some sort of like real scholarship to even be showing up today. I'm serious about that. And I want you all to know, even again, I know that there are certain people in every single room. I understand that there are certain people that are still like have a situation at home. So they're still going to turn it in later. And that's why I'm not going to get into the details of them. And they know that if they have an extension or whatever, for whatever reason that I've granted, that they're obviously not going to talk to other people like now at this point, now that the other people have turned into whatever. But I'm not going to get into that. Therefore, the physics details right now today. But I am going to say to each and every one of you that I still, at this point in my life, do not think physics is easy. And I definitely think it's a lot easier to teach than it is to learn. I mean, it's a lot easier for me to be me than to be in your shoes. I know that. And it's still, and I commend every single one of you who can get through an experience like this and still be standing and not like hate yourself or hate me or hate life or whatever. And so I very strongly want to say to all of you, and I'm dead, and I'd be saying this no matter what, before I look at the actual content, the actual questions and answers, before you actually get your grades back, you already have done something that's, and even if you're not done, you've already done something that is worthy of note and worthy of a compliment. Like, I don't think it's easy to be a science student, and I definitely don't think it's easy to be a physics student. So first of all, and I think you're all doing it with integrity and dignity, seriously. So first of all, I want to commend you on that. Second of all, I do have to admit, I mean, this is a failure of mine that I have to keep sort of apologizing for or acknowledging. There's no way these exams are coming back in 2 days. I mean, I think you probably have already guessed that. The reality is there's no way I'm having all these exams graded in 2 days. I really do hope to have them to you electronically sometime during the break, or at least before the end of break. I certainly hope to do that. They won't come back in 2 days. I will discuss them in more detail in 2 days. That I will do, because they'll all be into me. But I'm not going to have them graded in 2 days. But I'm going to tell you right now also, this applies to all of you in the room right now. I'm also going to tell you, sorry, I'm just switching. I'm going to tell you that that no matter, so that's funny. That's, well, believe me, I would like to. What was I going to say? It's all I can do to get my sons to do their work. Believe me. I mean, and that's the other. Anyway, whatever. But that's funny. I was just going to say. But as far as grades, and again, I know sitting in the class right now is difficult for some of you, I would think, or it certainly would have been for me if I were in your position. Even if you think you rocked it, it's annoying. If you think you rocked it, you're probably exhausted. And you probably want to be anywhere. That's funny. I see that too. You probably want to be anywhere but here right now. And I'm going to try to make it worth your while in a second, physics wise, and tell you why we still have to meet as a class until the end of the semester. But really, really, please know, I didn't know, my hat is off to all of you. I mean, I think in many ways, what many of you do is harder than what I did even when I was a student. And I did some hard things, but I had a hard time with them. I mean, I'm not here because I found it easy. I'm here because I found it fascinating. And I eventually went places with it, but not because I thought it was a joke by any means. But so as far in terms of your grades and school and all that, let me also say, and again, this is in the form of congratulations to those of you who really literally are done, and also as sort of motivation or encouragement to those of you who still have to tie things up and who had family issues and things, which I respect. And that is this: no matter who you are, I'm telling you right now that the midterm this midterm experience was your big responsibility to the class. No matter who you are, the final exam, which we'll get to, we're not going to discuss in detail today, but of course we are going to have a final, and this will be graded before you do the final. I mean, I hope, I pray. But when we get to the final, it will be a smaller experience than this. That I can tell you. Like, it'll be shorter, it'll be less material. It will be an opportunity to summarize and put the material together, but it won't be as long, it won't be as involved. For those of you who end up rocking this midterm, you won't have to be freshly stressed out over the final. The final will hopefully be a chance for you just to reinforce and cement the grade that you've pretty much already earned. And for those of you who, for whatever reason, don't end up doing well on this midterm, or do less well than you would like, and again, by the way, sidebar, I hope and believe that many of you will end up doing better than you think anyway, and I think the grades are going to work out, but more than you might think right now. But for those of you who don't do well on this midterm, the final is going to be meant more as an opportunity for you to repair damage to your grade. And in other words, what I'm trying to say euphemistically, and I think I did this with you guys, those of you who had me, I think I did the following in your Physics 203, but I will put a little bit more weight on whichever exam you do better on. I will not throw away an exam because we only have two. I'm not going to throw away a whole exam, but I'm going to put a little more weight on whichever one you do better on. And then, of course, all of those game turns and everything you do add a lot of points to your grade too. So in the final analysis, the whole idea is, if there's a way for you to get a good grade in this class, whether it's through the midterm or through the final or through all of your major participation and enthusiasm and engagement and concern, if there's a route, if you choose the route, if there's a route via which you could get a good grade in this class, then I'm going to then you're going to get a good grade in this class. Like, there's more than one path to the A, is what I'm trying to say. And I'm rooting as much as you all are for you, each and every one of you, to find whatever that path is. It may be this midterm. It may not for some of you. Some of you will have to work hard on the final. But the midterm is the big hump. The midterm, no matter who you are, will have been the sort of biggest, hopefully most stressful experience of the class. And then we're tapering down into the final. I just want to let you know of that. We don't have that much time left before the final. We don't have that much more material left. My goal, and I will get back to physics momentarily, my goal in this class and in the remaining classes is to do a little bit more material with you for sure, and show you how the last bit of material ties everything together and sort of hopefully allows you to see what the whole point of the class, and in some sense the physics sequence, was. Okay. I don't know if that makes any sense or not, but again, it's just a long way of saying I'm impressed that you've come this far. And I want it to turn out, and I think it should turn out to be a positive experience for all of us, like, even if it's through different means or for different reasons in different people's cases, hopefully. Now, obviously, if you do nothing, and then you won't do well. But I just forgot. I'm going to look in the chat in a second. And, I think there's two jokes in the chat, but I will look in the chat in a second. There was one other thing. But yes, I won't have this back for you in 2 days. I apologize, but I'm just, to be clear, I got to let you know that right now. That's not going to happen. But then hopefully during break or by the end of break, you'll get it electronically back, because I think break is next week. And if I'm wrong about that, you should let me know. And then we will start talking about the final. But physics, right. Yeah, okay. Have my son's grade in training. Believe me, I'm trying to indirectly train him in physics, but they struggle with school too. Like we all, it's part of the reason. Anyway, whatever. Okay. But yeah, Pokemon, I wish we could just be tested up. And if they gave me an exam on Pokemon, both of them, oh my God, like they both, anyway, whatever. Okay. Okay, so let me, was there something else? I feel like there's one other thing I had. One other thing. And again, I won't have the exams for you. I don't know. I'm just saying, I keep saying that I'm not proud. I'm just saying it to be honest. But I will say that, as mentioned before, Tuesdays is when I'm usually in my office, research lab, whatever, on the 4th floor. But sometimes it's not for a very long period of time. Tomorrow is another one of those Tuesdays where I will be there for a long time. Like, I'll be there in and out, of course, but I'll be there on the 4th floor from like 11 a.m. till like 7 p.m. or something like that. I mean, in and out. But if anybody has any concern or issue, please do feel free to stop by. Okay, yeah, please do, seriously, and I'll write again in the chat. It's hard to find, but I'll write again in the chat. It's not my office on the 5th floor. It's my research lab on the 4th floor, which is all I ever really use as my office. So no, feel free to stop by for whatever. And if you want to talk about your grade, you can. It just you won't have a grade on the midterm at that point, but whatever. Okay. So here we are. Okay. So now here is today. These are the 2 equations on the board right now, sort of summarize where we're going to end up going or getting in the next few classes. And I know that was the thing what Maisha said about again, look, if any of the YouTubes ever work for you, I am thrilled, of course, but whether wait, oh my God, that's fun. Oh my God, that's funny. Okay. I don't know how you guys do that unless you're zooming on well, I'm not going to ask. Okay. You're so much more advanced with Bitmojis and everything than I am. But one thing also is from the questions that I was getting about the exam and stuff, again, maybe I should, oh, it is? Oh, I guess I sort of knew. Did I know that? Oh, I guess I sort of. Okay. Well, anyway, oh yeah, no, I guess I did. I guess I did sort of know that, but okay. No matter what, even if I figured it out, you would then figure out the next thing that'd be ahead of me. But like that. Okay, yes. Well, I want to get back to the material, but and I hope that your labs are somewhat related to the lecture, and I want to keep them that way. And I actually want to hear about something about your lab in a second. One thing though, from the questions that I was getting over the weekend about the exam, and you could tell from the corrections that I posted or the clarifications that I hope you saw, anything that I posted about that exam while it was happening was the result of somebody asking me a very good, thoughtful, observant question, which I totally appreciated. And there are some of you that I get to know better just from those interchanges than I ever do in class. And that's great for both of us. And it's impressive. But I want you to know also that one of the reasons that I do the exams the way I do is one thing I definitively discovered in college. I mean, when I was a physics major in college, one thing that I noticed that I always thought was weird or somehow I was doing something wrong, but it turns out no, like it's true that I would learn a ton of material just in the process of studying for an exam or often taking the exam. Like, and I always felt like, oh, that I'm so behind or I'm cheating or something like, oh, I thought for a while that exams were supposed to be finding out how much I knew going into the exam. And I thought if ever I was figuring things out in the middle of an exam or while at the last minute studying for it, I thought I was missing the whole system somehow, or I was cheating the system, or I was a loser or something. And I was like, oh, they were trying to find out what I already knew, but instead here I am figuring it out right now. But it turns out, no. A lot of the point of an exam is to force us to put together things that we had not put together until the actual exam is occurring. I could tell from some of your questions that you were sending me this weekend, some of you, or this morning, whatever, that you were figuring things out for the first time right now while the exam was out. And there's no shame in that at all, as long as you do figure them out. That's actually part of the purpose of an exam. That, like, really, so if any of you did feel like you were actually, that things were coming together at all, or between the lectures and the labs or anything, then Quark bless America and Quark bless us all. And it's another good reason that I'm glad we had the exam. Like, if that's not you messing up or cheating or me, like, that's the point of an exam. So I don't know if that makes it more pleasant, but it is true. Who is Quark? I'm kind of, well, Quark, I don't know if that's a joke. A quark, okay, sidebar, and then I'm going to go. A quark is a subatomic particle. A quark is a thing in physics. A quark is a tiny particle of which subatomic particles are. Yeah, like, okay, this is a sidebar, but actually this will get us, okay, this will get us into the topic of today, actually. Wait. Yeah, oh, no, I'm not. I'm sort of making a joke every time I say that, but so I will say this, quarks are what make up. Yes, exactly. and this will get us into the topic. Okay, so I'm just going to say this at the risk of frustrating everybody else in the room, but it'll get us into our final topic of the semester. Our final topic of the semester is electricity. Let me just say that, okay? Our final topic of the semester is electricity. In fact, here we go. Yeah. Our final topic of the semester is electricity, and I'll explain why or how it fits in and whatnot in a minute. And that should, in fact, also be the final thing that you either will be or already are studying in the lab. Maybe you could tell me in the chat whether you've already started in the lab or not. I'm not sure. It differs from section to section. But electricity is our final topic of the semester. Electricity ultimately has to do with electrons. It has to do with electrical charge. Charge is contained in electrons and protons. Now, it tends to be electrons. Protons tend to be trapped in the nucleus of an atom. So you can't really move protons around unless you move the whole atom around. And that ends up meaning moving materials around. But electrons, as you all know from chemistry and from other science classes, electrons can be freed from atoms. Atoms can be ionized, as you know, turned into ions, right? Atoms can give up and often acquire electrons. So electrons are these little particles that can move freely about, disassociated from any one particular atom, disassociated from any particular bit of material. They can just move freely, and they do through certain types of materials, such as metals, known as conducting materials. We're going to study for the remainder of the semester the impact or the effect or the consequences or the ideas surrounding the interaction among these electrons, these charged particles. We're going to be studying how charge interacts in the universe, particularly in the context of electrical current, and electrical circuits, which you study in the lab, and electrical field, which you'll study in the lecture for the remaining period, okay? Sidebar, electrons are what they are called elemental or elementary particles. Like electrons don't really get broken up into anything smaller than electrons. Electrons are as small as it gets. In fact, sidebar, electrons are in fact point particles. Like electrons have mass, but they don't have any volume. They literally are like Euclidean points with mass, which is bizarre unto itself. But electrons are as small as it are. Just you can't get smaller in size than an electron. But protons and neutrons, which are contained in an atom, contained in the nucleus of an atom. Protons and neutrons, we believe, have size. They can be broken down smaller, and they're broken down into smaller particles that are known as quarks. Now, we are totally not studying quarks in this class. It's just random that I always bring them up, but as long as you're asking, quarks are the elemental particles that are put together to make protons and neutrons, for whatever it's worth. That's what quarks are. So whenever I say quark plus America, I'm just referring to those. But we here in the class are now, from here on in, going to be, there are different quarks. Good, you know that. You know about like up and down quark. You're talking about. There are different quarks. And that's a whole other subject. They don't. Do they all have charge? I get confused about that. I'm not. That may be true. I always get confused if quarks have charge or not. I'm not sure, but there are different. Yeah, there's like up top quark, bottom quark, but in this class, we're concerned with charge. We're not concerned with quarks. We're not concerned with neutrons. In this class, for the remainder of this class, we're concerned with protons and electrons, specifically electrons, or like most primarily electrons, because electrons can be separated from atoms and moved around by themselves, as in through wires, as in through circuits that we call electrical circuits for precisely that reason. Okay, so I'm going to shift. Let me just erase it. So let me, so what this thing on the sheet says, we're going to now talk about electricity for the remaining time. And the reason we're going to focus on electricity is the same reason that we made such a big deal about waves. That ultimately the purpose of this class, the focus of this class, is unthingy motion, right? This class is ultimately, it's supposed to be using the same principles and practices that we used in Physics 203, the same principles and practices that we developed for measuring, analyzing, and predicting motion of stuff through space and time. Like that's what physics is, motion of stuff through space and time. But in Physics 203, the stuff that we analyzed moving through space and time was material, particular, discrete, massive, countable, tangible stuff. In Physics 203, no matter what topic you were doing, no matter what professor you had, in Physics 1, we were studying trajectories of particles, like a baseball goes from me to you, or even a planet goes from here to there. Or if you like, or an atom, like even could be something very, very small, could be something so microscopically small that it seems invisible, but still like could be an atom, could even be an electron, by the way. But whatever it was that we were talking about in Physics 203, we were talking about objects going from here to there, and all the equations and all the problems that we solved, we were always assuming, believing, and knowing that the object going from here to there literally was an object with a boundary, like say, for example, a baseball. And what makes a baseball an object? What makes a baseball ultimately something that we would call a particle? Well, what makes a baseball a particle? I mean, truthfully, a baseball is many, many, many particles put together. I'm not trying to say that it's only one, but the reason we call a baseball a particle, and the reason that we say that when a baseball moves from me to you, the reason we call that particle motion is because when a baseball goes from me to you, something particular goes from me to you. Something that is a thing that has a boundary, that is separable and distinguishable from the rest of the world, right? Like picture a baseball for a minute. Anything in the world is either part of that baseball or it isn't. Like it's clear, like there's an outside to that baseball and there's an inside. And you could say that the baseball is made of many, many atoms, and that would be true. Like I'm not saying the baseball isn't made of lots of course, a baseball is made of lots and lots of little things inside it. But the point is that every one of those little things is either in the baseball or it's outside the baseball. It's very clear to us that the baseball is a bounded, discrete, identifiable, pointable, like there it is, there's the baseball thing that has mass. And to go back to the beginning of our semester, remember a baseball, really when I say that it's a particle, and I say all of the stuff I just said, that it's like bounded, discrete, countable, identifiable, distinguishable, what I'm really massive, what I'm real tangible, what I'm really saying, really that makes a baseball a particle and makes baseball motion particle motion. And again, baseball is just an example. It could be a planet, could be a hammer throw, whatever. But what really makes it a particle is that the center of the baseball is at one point in space at one point in time. It is not in 2 points in space at one point in time. The baseball is not spread, like the center point of the baseball is not spread out in space. It's not confusing that the baseball is not here and there simultaneously. Furthermore, the center of the baseball it occupies 1 point in space at one point in time by itself. The center of the baseball cannot occupy 1 point in space at one point in time while also some other point of mass occupies the same point. It cannot co-occupy 1 point in space with another object at one point in time. If another baseball comes in toward the first baseball, they don't mesh together into one. They don't meld. They don't share. They don't constructively interfere or destructively interfere. They bounce off one another. They have a collision. They don't share space, right? So what makes a particle is that it's not in two places at once, and it's not in one place with another thing at once. And when the baseball goes from me to you, it literally goes from me to you. Like first the baseball's here, then the baseball's there, then the baseball's there, then the baseball's there, right? So every single point in between me and you, at some point or another, the baseball occupies. That's what we mean by particle motion. Particle motion is when a discrete, identifiable particle actually makes a journey from one location to another, and in fact, passes through all the intervening points. What this class is really ultimately concerned with, although it took us a long time and a lot of math to build up tools for the following, but what this class is really concerned with is other types of motion that are immaterial, non-particular, like, again, and I hope you've gotten this point by this time, I'm just summarizing or reviewing or refreshing or whatever, like, or our ultimate most recent thing before you took the exam was thinking about something like sound. When sound goes from my mouth to your ears, and again, I'm not worrying about the internet right now, I'm just assuming we were both in my office or in a classroom right now, and I'm shouting, when sound goes from my mouth to your ears, that is a real motion, is absolutely real, scientific, observable, measurable, analyzable, quantifiable, predictable motion. Like when sound goes from my mouth to your ears, we absolutely could talk about how much space was traversed. We could talk about how much time elapsed for that motion. We could put one quantity over the other, get something called a velocity, a phase velocity, or a propagation speed, or whatever you want to say. And then we can use that speed to plug into equations and make other predictions like, oh, if you're twice as far away from me, oh, I guess the sound will take twice as much time to get to you. We could do all the physics that we ever did, analyzing the rate at which sound travels from me to you, yet, please remember, and I apologize if you've heard this a million times, or if you feel like you've gotten this a million times. I mean, I sort of apologize, but I sort of don't, because good, that means you're getting something super important from this class. When sound goes from me to you, there is no individual, discrete, countable, identifiable, or massive or tangible item that in any way goes from me to you, right? That's super truth. That's really a heavy, to my mind, fascinating point to realize that when sound goes from me to you, something very real is moving through time and space, and something very scientifically analyzable is happening, but nothing material is moving from me to you in space. Nothing thingy, something very unthingy is moving from me to you when sound goes from me to you, and sound just being an example of wave motion in general. But right, like remember, and I'll say this one last time and then we're going to go on, but just again, to sort of tell you the whole purpose of this course and to tell you why we're going to spend the rest of our time on electricity and associated ideas, is that when a sound wave goes from me to you, certainly there's motion, and certainly what is happening is a bunch of air molecules that are between you and me must be moving in a very, very regularized, very, very precise, specific, highly mathematical way. A bunch of air molecules are absolutely moving in a pattern of patterns, to be sure. And without the air molecules there would be no sound. But even with the air molecules there isn't automatically sound, i.e. air is not sound. Air is necessary for sound, but air is not sound. B, even though when sound goes from me to you, even though air molecules all must be moving in a very specific way for that to be the case, there is no air molecule that goes from me to you when sound goes from me to you. That's an enormous point. Let me just say one last way or one last time. When sound, in order for sound to go from my mouth to your ears, a bunch of air molecules must move in a highly specific, highly mathematically ornate way. But in order for sound to go from my mouth to your ears, no individual air molecule need go from my mouth to your ears. Even though air is the only thing moving, no air actually makes the journey from my mouth to your ears. And furthermore, another way to put it is, I don't care how powerful your microscope is, I don't care how advanced your technology is, you can look as closely as you want at that air in between those air molecules throughout the whole medium between my mouth and your ears, and you're never going to find a particle of sound. There's no such thing as an item of sound. There's only a such thing as air molecules, which are not sound molecules. They're just air molecules. But if each one of them shakes in a very specific way, and they all shake in a certain space, in a certain time, then the whole phenomenon together creates this motion called a sound pulse, which is a phenomenon, not a thing. Sound is an example of something that matters, but isn't matter. Something that moves through and affects the material world, but is not material. Sound is an example of an immaterial motion. We've spent most of this course trying to get to the point of understanding how such a thing as sound could exist without being a thing. That is and that's why it's not a coincidence that the math got more abstract than last semester and the ideas got more abstract, and why it took us so long to build up all these steps that, all these trees that are easy to lose for the forest. We're trying to use traditional methods of analyzing motion through the material world in order to ultimately understand how there could be an immaterial motion in the material world. Sound is our primary example because it is true and real, but it's so common and so familiar and so part of our daily lives that it's impossible not to believe in it, right? But sound is just an example. The rest of the course, we want to deal with at least one other or two other examples and see how it can get even more abstract than sound, okay? So the next example is electricity, whether it be electrical currents that you're going to deal with in the lab or electrical fields that you're going to deal with here in lecture. Both are examples of immaterial motions through the world. Both are examples of flow of information, propagation of information, propagation of energy, rather than trajectories of particles. Okay, so that's like why we're doing them. Again, electric current is for the lab, electrostatic field is for here. So let's now start talking about, so we're going to get to field. First, in order to get to the concept of field, I have to lay down some basics or fundamentals about charge and force. Like field ultimately is a concept that comes from the concepts of charge and force. So let me first talk to you about force. Okay, and charge. Okay, so I'm going to start with this idea. If you have any 2 point charges in the world, if you have any 2 point charges, call them Q1 and Q2, and make Q1 a capital letter and Q2 a lowercase letter, just to make the distinction even clearer. So you've got 2 charges in the world. And if they're separated by some displacement, then one will automatically exert a force on the other. One charge will, so you have any 2 charges in the world separated by some displacement, one charge will automatically exert a force on the other charge, and the other charge will automatically exert a force back on the one. Okay, I'm going to unpack this in more detail, but I'm starting with that. and stop me if there are any questions. But okay, so that's just a statement of English. Let me try to unpack it a little bit more in terms of equations and stuff like that. So first of all, let me remind you what a force is. Okay, I mean, I also have to answer the question, what exactly do I mean by charge? But before I even get to that, let me remind you what a force is. A force is not something that an object has. It's not a property of a single object. Oh, sorry. Yeah, absolutely. Yes, yes. Okay. Sorry. And I'm gonna hold on. I'll wait for a second. Okay, cool. No problem. No problem. Okay. And I got myself distracted for a second. Okay. Okay. So a force is not a property of one single object. A force is an interaction between two particular objects, like always in physics, no matter how abstract, like no matter what kind of forces you're talking about, whether you're talking about tension in a rope or the normal force exerted by a wall or friction force exerted by a floor or the gravitational force exerted by gravity, by earth or anything, a force means an interaction between two objects. And let me say, the word interaction is actually a great word. I didn't realize for the longest time that in physics, the word interaction is almost used interchangeably with the word force. Interaction means force and force means interaction. And interaction is a great word, really, because it literally does mean interaction, by which I mean, when I say interaction, I mean inter tells me there's got to be two things involved, and there really do. For any force that you're ever going to talk about in physics, you can never say the baseball bat has a force. You have to say the baseball bat exerts a force onto the baseball, or vice versa. The baseball exerts a force onto the baseball bat, or something like. Okay, there's always two objects, and they're always objects. You can't ever just like say gravity pulls on the cup. Well, what you mean when you can say it. But what you mean when you say gravity pulls on the cup, it's a shorthand for saying the gravitational force exerted by the earth pulls on the cup. You're really saying the earth pulls on the cup. So a force always, and I'm saying this seriously, like if you're ever trying to picture a force and you can only picture one object involved, something is wrong and you're not picturing a force somewhere. But also force is action. Force is therefore, the two objects, action. By action, we're saying that force is just that. It's an action. It's like a verb. It's not a noun or an adjective. It's an action. So meaning that whenever one object exerts a force on another object, it is doing something to the other object. Ultimately, it's always, 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 always a push or a pull. Now, you don't always see forces. Forces sometimes are happening through contact and sometimes they're not, and we're going to talk about that. And sometimes the force it seems to be measurably effective, and sometimes it doesn't. What I mean by that is, according to Newton's second law, F net equals ma, the result of it, once you add up all of the forces acting on an object, once you add up all the pushes or pulls happening to me from wherever they're coming from, and they could be coming from all kinds of different places, but they've got to be coming from places. Once you add up all the pushes or pulls happening to me, then the sum total of that, the net effect of all that, taking into account minus signs, is that I will accelerate. accordingly, right? So the observable, measurable effect of forces is acceleration, but acceleration is the observable effect of net force. So as you know from physics 1, if a force is pushing me with 10 newtons to the north, and at the same time, another force is pushing me with 10 newtons to the south, right? Like in other words, if you're pulling me that way and your friend is pulling me from behind the other way, well, then the net force on me is going to be, there's all these forces on me, but the net force on me will be 0. So I won't accelerate anywhere, right? So you'll both still be exerting forces on me, but we won't really see anything happen necessarily. What I'm saying is forces are not things that they're not very easy all the time to measure directly. They are not results. They are actions. A force is a push or a pull, whether or not it results in acceleration. So a force is an interaction between two objects, and it's symmetric, meaning Newton's third law. If I pull you, you necessarily pull me. Pull means toward, and push means away, right? So if I pull on you, that means I'm trying to accelerate you toward me, whether I succeed or not. I'm trying to accelerate you toward me. If I do that, then necessarily you are trying to accelerate me toward you. And similarly, if I push you away, you are necessarily pushing me away with the same magnitude, just in the opposite direction. A force is a symmetric interaction between two particular objects. Okay, that's what a force is, whether it's normal, tension, friction, gravitational, electrostatic, whatever. A force is a symmetric interaction between two objects. Oh, and I should also say, to be clear, a force is the units that forces are measured in. The units are newtons, right? And from Newton's second law, 1 Newton of force equals 1 kilogram of mass times 1 meter per second squared of acceleration, for whatever that's worth. Because like F net equals ma. Okay, so forces are measured in newtons. They're interactions between actual objects, masses, particles. Okay. Now, sometimes the force involves contact, physical touching. Sometimes it does not. One case where a very real, calculable, predictable force acts without physical contact is the case of what we call universal gravitation, Newton's law of universal gravitation. Now, so I want to talk about universal gravitation for a second. Universal, like gravity throughout the whole universe, including the Earth, but not restricted to the Earth. Now, to some of you that I'm talking, this will be old news. You might have seen this depending on who your professor was, you might have seen this in Physics 203, or you might have seen this in high school, or for some of you, you might never have seen this before. It's fine either way. I know it's different for different people in the room, but I'm telling you now, so I'm either reminding you or I'm telling you now that there's a law called Newton's law of universal gravitation that says for any two given, so if you read it from the bottom, if you sort of read this sheet upside down, it says if you have any 2 points of mass, call them M1 and M2, or capital M1, lowercase m2. If you have any 2 points of mass, bits of mass, any amounts of kilograms that could be taking up very, very small amounts of space. If you have any 2 bits of mass and they're separated by a distance r, one mass will automatically exert a force on the other mass automatically, just by virtue of them existing. Like it doesn't have to reach out and grab the other one. It doesn't have to tie a rope or like set up a magnet or anything. Any bit of mass that's over here automatically pulls, exerts a force on any bit of mass over here. It also automatically exerts a force on any mass over here. And it also automatically exerts a force on any mass over here. Every single bit of mass in the universe, evidently, is automatically pulling on every other bit of mass through the universe. They're all interacting via this force that we call gravity. And this force called gravity happens to always be, it seems, a pulling force. It's always a pull for whatever reason. It's always a pull, and that's actually why there's a negative sign in the equation to mean pull. I'll get to that, or you'll see that more as we develop this. But what the equation, so first of all, just qualitatively, it seems that since Newton, we believe that all masses, all bits of mass in the universe are automatically and necessarily and all the time pulling on all other bits of masses in the universe. That's a big thing to believe in. I am saying I'm saying we believe in it. I'm also saying that it's true. I'm not at all right now pretending to say that it obviously makes sense or that we should believe it or that, of course, you would think that this would be true. Not at all. It doesn't obviously make sense at all. And we're going to talk more about that. I'm just saying it appears to be true. When I say it appears that things we've known for thousands and thousands of years that for whatever reason, all things seem to be pulled toward the center of the earth. If you let something go, if you don't support something, it seems to always fall down automatically toward the center of the earth. It seems like the center of the earth is automatically always necessarily pulling on every bit of mass that comes anywhere within its neighborhood. We've noticed this, just noticed it in life for our whole lives and for thousands of years, that things tend to fall down toward the earth. I'm not saying that should be the case. I'm not saying that does make sense. I'm just saying it seems to be true. Well, it turned out in the late 17th century, in the early 18th century, standing on the shoulders of some other giants, Newton sort of connected that realization, that phenomenon that things are always falling toward the earth. He said, he followed sort of in the footsteps of Galileo and said, we've been wondering for so long, like, why does the earth have this special property that it pulls everything toward it all the time? Like, what is it about the earth that makes it specially pull everything toward it? And, Galileo had just come right before Newton, and Galileo had given us this whole new worldview of physics that you and I, you in the room, you and I have spent a full semester of Physics 203 and a half a semester of 204, realizing from Galileo, we all realize, the earth is not special. The earth is not sitting still at the center of the universe. The earth does not have its own physics laws that only apply on earth and that have to be completely changed and reformulated to explain motion through the heavens. It turns out since Galileo, the way we view the world is we view the earth as just a part of the whole universe. We view the earth as not sitting still at the center of the universe. We, since Galileo, believe nothing is special or necessarily sitting still at the center of the universe. We think since Galileo that it is in heaven as it is on earth, that one set of laws governs both, and that the earth is just another rock hurtling through space, and that all of space is governed by one set of physics laws, and that you can do physics from any coordinate system you want and still get the same right answer to physics problems. Well, in that spirit, Newton, along with a bunch of other things, Newton put together a bunch of astronomical data, a bunch of measurements and numbers that we had applying to motion of the heavenly bodies, motion of planets through what we now regard as our solar system, took a bunch of measurements and numbers and things related to orbits and eclipses and predictable events in the sky. And Newton took the spirit of Galileo and said, oh, I see, the earth is not special. It's not that everything is always being pulled gravitationally just toward earth. It's that everything in the universe is being pulled toward everything. That just like everything near the earth is being pulled toward the earth, even including the earth's moon, the Earth itself is being pulled toward the sun, and the planets are being pulled toward the sun, and that there's apparently a force called gravity, which is exerted by any one object in the world on any and every other object or mass in the world, in the universe. And apparently the gravity between some things like the sun and the earth is stronger than the gravity between other things like the sun and well, what we would now regard as Pluto. And Newton put the numbers together, and other people did as well, and came up with a discovery or a statement or claim that, okay, for any two given objects, for any two given points of mass in the universe, call them M1 and M2. If M1 and M2 are separated by distance r, then M1 will necessarily pull on M2 with a force measured in newtons that is, on the one hand, directly proportional to the mass of M1. That is, so i.e., if the bigger the mass 1 is, the bigger this force, this pull will be, but also directly proportional to the mass of M2. So the bigger that mass 2 would be, the bigger this force will be. So notice you've got M1 and M2 in the numerator of this fraction here in this equation on the sheet. But also Newton said the magnitude of the force will be inversely proportional to the square of the distance between M1 and M2. Now that sounds very obscure and very like, whoa, wait, what? And in some ways it is, but in some ways we're going to unpack it and see that it isn't. But the shorthand version of it is it's saying the heavier either or both objects are, the stronger the attraction will be between them. But similarly, at the same time, the closer they are, the smaller r is, the bigger the attraction will be between them. Like F is inversely proportional to the square of r. So if r is big, F is small. If r is small, F is big. And apparently F is inversely proportional not just to r, but to the square of r. So if two objects suddenly get twice as far from each other, the force that one will exert on the other will get to be 1/4 as intense as it was. Right now, I am not saying so. So I should say. So what I'm trying to say so far. So far, what I'm saying is that there's this force of gravity that any one point of mass exerts on any other one point of mass, and that force of gravity is directly proportional. That symbol out, that little symbol means directly proportional. So the force of gravity is directly proportional to the magnitude of one. It's directly proportional to the magnitude of the other. It's directly proportional to the inverse, so it's inversely proportional, of the square of the distance between them. And what does directly proportional mean? Well, we've seen it now a million times with the wave equation and everything else in this class. Directly, if I say that y is directly proportional to x, that means y is equal to x times some constant, right? That's what directly proportional means. So the constant in this case is this letter capital G. I'm not saying that you would have known this. I mean, you might, but I'm not saying you should have known this number. I'm certainly not saying you have to memorize this number. But I'm just saying that there is a constant, a number that happens to be very, very tiny, and it's called the universal gravitational constant, capital G. This is not lowercase g. This is not the 9.8 number. This is capital G, the universal constant of proportionality between the gravitational force and the relevant masses. The number happens to be 6.67 times 10 to the negative 11, tiny number. Newton's meter squared divided by kilogram squared. Those are the units. Now that looks very obscure. Those units look like crazy maybe, or look impossible to memorize maybe, but look carefully at those units. They actually not only make perfect sense, but they're actually And they're not only exactly what they would need to be for this whole thing to make sense, but in fact, they sort of even show you why there has to be a G in the first place. The point is that any one mass in the universe necessarily exerts a force on any other mass in the universe. And it's proportional to the masses divided by the distance squared. The thing is, force is measured in newtons. If you multiply a kilogram by another kilogram and divide by meters squared, you don't get newtons. In order for this whole thing to work out properly and actually give you a force measured in newtons, the mass and the distance squared have to be multiplied by some constant whose units are newtons times meter squared divided by kilogram squared. In other words, the meter squared in the numerator of G cancel out the meter squared in the denominator of the whole fraction, and the kilogram squared in the denominator of G cancel out the masses on the top of the whole fraction. So the meters squared cancel out, the kilogram squared cancel out, and you're left with newtons. That's actually largely what that number there is doing. It's just making it so that the units work out. Ultimately, I'm saying that any and every one bit of mass, every and any bit of mass in the universe automatically, necessarily, and always pulls on any and every other mass in the universe with a force that we call gravitational and with a number of newtons that's determined by this equation. Okay, that's what masses do to other masses throughout the universe, and this will work. Gravitation, this force, gravitation, is exerted at a distance. Sometimes it's known as a fundamental force because you don't have to do anything to make this force occur. If you are a point of mass, if you are any bit of mass at all, you just exist, you're going to exert this gravitational force. You're going to start pulling on other masses at a distance, like wherever they are, you're just going to start pulling on them. And if nothing else were ever happening in the universe, everything would come together because of this. At a distance, meaning you don't have to do anything to make it happen, and you don't need to be touching. There doesn't have to be any contact at all between the two masses for this to happen. And furthermore, even if there's stuff in between them, even if there's like wood between the two masses, the gravitation will still happen. The gravitation occurs through empty space or through matter just as easily either way. It doesn't require any physical contact or touching. It happens at a distance, and therefore it's sometimes known as fundamental. Okay, that's gravitation. Now, in theory, a lot of you already knew that. I mean, I know that some of you didn't, but some of you did. But that, in theory, is an old thing from classical mechanics, from physics 203 or from high school or whatever. It's the way masses automatically interact with other masses. And again, it explains why things fall toward Earth, but it also it relates to how things fall toward Earth, but also just as much describes how Earth falls toward the sun, or the sun falls toward the center of the galaxy, et cetera, et cetera. Okay, that's masses. Now, what I'm here to tell you, in theory, that's almost background, but it's just true. What I'm here to tell you in the remaining 6 minutes that we have, and then, on Wednesday, what I'm here to tell you is that something very, very similar, in fact, mathematically identical, occurs between point charges. That for any two charges in the universe, any bit of charge over here will automatically pull or push any bit of charge over there in a manner that is mathematically identical to this. Only with charges, it can be a pull or a push. Charge, I don't know exactly what charge is any more than do I know exactly what mass is. It's just it's a property of stuff in the world. Protons are made of charge, or have charge, or are charged, and electrons are made of charge or have charge. In fact, one proton, whatever charge is, I know that one proton has the exact same amount of it as one electron. A proton has one certain unit of positive charge, and an electron has one amount of negative charge. And the fact that charge comes in these two different varieties is the one thing that's sort of different about charge from that of mass. Charge seems to come in two different varieties. And as you know from chemistry and so forth, like charges seem to repel and opposite charges seem to attract. And that's why we use this positive and negative convention, because it works out. It's a nice connection, because if you've ever noticed, just like in math, like a positive times a positive equals a positive. A negative times a negative also equals a positive, whereas a positive times a negative or a negative times a positive equals a negative, right? So we use positives and the negatives to deal with charges, because the same thing applies to charges apparently. Like a proton and a proton repel, an electron and electron also repel, but a proton and electron seem to attract, and an electron and proton seem to attract. So if from here on in, if we always use negative to mean attraction, and we use positive to mean repulsion, it all works out nicely, because likes, like two positives will create repulsion, two negatives will create repulsion. And it's just a convention. But the reason we call, like we could have called protons blue and we could have called electrons red or something like that, but we call them positive and negative because it nicely works out with this idea that likes always repel and opposites always attract. Okay, so it turns out the charges in the world all attract and repel each other according to the same type of math as the math that shows us what masses do each other. So next page, I'm saying in the world, if you have two charges, instead of two masses, if you have two charges, Q1 and Q2, then there's this law, then a law called, and you might know this from chemistry, somebody, this is called Coulomb's law. This is Coulomb's law, or the Coulomb force, or the Coulomb interaction. It's just like, and I know we have 3 minutes, but we're just about there for today. What I want to drum in today is, if you have any picture in your mind about how masses automatically pull on each other, and if you have any picture in your mind that the heavier a mass is, the more it will pull on another mass, and the closer it is, the more it will pull on another mass. Point charges do the exact same thing. And you might say to yourself, well, okay, I sort of understood with mass, but when you say about charges, like I can't really picture a charge, that's a little harder to picture. I agree with you. Charge is a little bit harder to picture than mass. But what I'm really asking you to picture when you picture charges, picture little protons or picture little electrons. Just picture these tiny little shimmering particles. And we're not worried about how heavy they are now. We're just worried about how shimmery they are now. Now, it turns out that if you have proton or positive, if you have charge over here and charge over there, it will pull on each other or push on each other in a manner that is directly proportional to how charged each one is, and in a manner that is inversely proportional to the square of how far apart they are, just like gravity, okay? With gravity, the things pulling each other are masses measured in kilograms. Here, what's pulling and pushing each other, and I know I have 1 minute left and then we're done. What's pulling and pushing each other here are charges measured in coulombs. The unit of charge you may or may not know from chemistry is called a coulomb, as in Coulomb's law. And just for perspective, it would be nice if one proton literally had exactly one positive coulomb of charge and one electron had one, but they don't. Just for historical reasons, it turns out a proton, if you're going to measure its charge in coulombs, a proton actually has a tiny, tiny, tiny amount of charge. Actually, a proton has approximately 1.60 times 10 to the negative 19 coulombs of charge. You don't have to memorize that. I'm just telling you that for perspective. But when I picture charges, point charges, I picture little protons and electrons. And if I picture 1 coulomb of charge, I'm actually picturing like 16 quintillion protons all jammed together in a tiny space, making 1 coulomb of charge. They will pull on 16 quintillion electrons with a force that's determined by how far away they are. And also, and this is the last thing I'm saying because it's 420, the force function, the description, the law here, this is Coulomb's law of electrostatics, is just like gravitational law for masses. But the one last thing is the constant here is different. The constant in gravity is capital G. It's a tiny number, 6.67 times 10 to the negative 11 newtons meter squared divided by kilogram squared. Here, it's newtons meter squared divided by coulomb squared to cancel out the units of charge. And the number here happens to be a huge number, 8.99 times 10 to the 9th, just demonstrating that when all other things are equal, actually the electrostatic interaction happens to be a lot stronger actually than the gravitational interaction, but that's just what it is. So that's all I'm saying. So I'm just saying right now, there's forces in the universe that are called fundamental that happen, that occurred just because things exist. Because mass exists, there's gravitational force. Because charge exists, there's an electrostatic force. And they both happen through distances, at a distance, through space. That's all we got to say for today. Again, congratulations on wherever you are with the exam. Thank you both so much. I will see you on Wednesday, or if you stop by tomorrow, I'll see you tomorrow. Thank you for your attention. You're a wonderful group. Hey, yes, have a great night. Okay, have a great night. Thank you. I'm turning off the ring. Thank you, Jayla and John and everybody. Thank you. I'm turning off the. Thank you, May. I appreciate it. I do. I really do. Okay, I'm turning off the recording.